Okay, so let's talk a little bit how to work with graphs and networks using programs. So here we're going to look at how to do this using Python. So in particular, we're going to focus on unweighted, undirected networks. And let's look at how we'd work with network data ourselves in maybe a little bit of a naive way. We're going to build up some functions, and then we'll dive in and see what existing libraries can do for us in Python. So to get started, just like with numeric or tabular data, which has a design matrix, right? We need a data structure to store our network data. So we're going to have to store it in Python in some way. And we want to interact with it easily and write it out to files, right? To share between different programs. Those are our requirements. So to get started with a network, you can think of networks, they have nodes and edges, nodes and links. And so we can think about each of the nodes having an ID number. Here with n nodes, we could just say that those ID numbers are incremental, so from 0 to n minus 1. And in Python, right, that could be range of n. But we could also use names. So if we're 0 to n minus 1, I'm thinking, we could store things in a list. But if we want to use names, right, we could actually use a dictionary. We only need n unique items, and dictionaries are fast for looking things up because they're a hashed data structure. So if we use a dictionary, we need to store all of the node names as the keys in the dictionary, and the values are going to be the edges. So we can make a dictionary that maps a node to all the neighbors. So here, this is a fully connected network, which is a dictionary. Each key is a node, and each value is the other nodes that are the neighbors of the given node. So here, Alice points to Bob and Carol, Bob points to Alice and Carol points to Alice and Bob. So there's a few things we can notice about the way we've set this up already. In particular, this is a directed network. We can plug in a node and we can get the list of neighbors. So here it's fully connected, and it's really easy to get the degree using our simple storage here. So if we want to compute the degree, we just need to look at the length of the neighbor list. So here we just return the length of the neighbors of that particular node. So this is pretty easy. One caveat, we're using lists to store neighborhoods. So we could have duplicates, right? So here we could actually have multi-edges, which, is maybe a feature or a bug. I would think of this as more of a feature, but we have to be careful when we're creating these. So there are two links as a multi-edge, and may or may not want it. We can also create self loops. So Alice can be a neighbor of herself. One thing that I mentioned earlier, this is a directed structure that we created. So Alice points to Bob and Carol here, but Bob doesn't point back to Alice. So here Alice is a neighbor. So here Bob is a neighbor of Alice, but Alice is not a neighbor of Bob. So we can have that with this network structure as we've defined it. So here there's no out degree for Alice. So, depending upon how we're using this, right, we might need to be careful to not make multi-edges or to make sure that if we want things to be undirected, that we add on both sides of the adjacency lists here. So the Python dictionaries are case sensitive when strings are used, so just one other thing to know. So basically, if we want to make sure that these conditions hold, we don't want to interact directly with the network data structure. Here, if we're just adding and subtracting things from a dictionary, we could easily go wrong. So let's go ahead and build up some functions that allow us to work with this data structure and begin to work with networks. So if we want to add a node, pretty simply, we could define a function which takes the graph, here just the dictionary, and insert a node. Here, we're going to be careful not to overwrite a node that exists. So if a node exists, if a node already exists, then we're not going to add it to the graph. But if it doesn't exist, we'll go ahead and add it with no neighbors. Here, it'll modify the graph in place. So there's our add node function. Right, we can go ahead and add a node to our simple network here. We can add Dan. So here, Dan has no neighbors. We could also add an undirected edge. So here, an undirected edge means we'll have to have it go in both directions. So create the nodes if they're needed, just like the add node function. And then we want to insert the length on both sides, right? So here we're doing a lookup in the list. So that's one thing to note, is it could be slow. So we're checking if J is not in G of I, so we're looking for J in a list, and then we'll append it to the list. And similarly, we go on the other side. So G of J, we append I. So we've created the bidirectional link here. So it's an undirected edge. So here we can go ahead and add an edge between Dan and Carol. Dan now has a friend. He has a neighbor, Carol, and Carol also links to Dan. So there we go. Dan is now part of this network, not floating off by himself. So things are getting a little more complicated. We're adding nodes and edges. We need to make sure that we create the ends of a link. We also need to insert a link in both directions, and we need to make sure not to create a multi-edge if the edge already exists. So we don't want to create multi-edges accidentally in this situation. If we want to remove a node, right, we can do that too. If we want to remove a node, we need to first remove it from the neighbor list of all of its neighbors and then remove it. So this one's also a little more complicated. We can go ahead and get the neighbors and then go ahead and remove it from all the neighbors. Here, we're relying on the fact that our network is not directed, right? So we're actually making sure that the I exists in G. If it didn't, right, it would raise a value error because it might not be in that list. So we could check that too. But here we'll go ahead and remove Alice, and we can see that Alice is now gone and also gone from all the neighbor lists. She's totally gone from the network. So we have these. We had to take a lot of care to make sure that we were working with an undirected network. A directed network would actually be a little easier to program up. But we've got a collection of functions going, and we can now kind of work with the network, add and delete edges, add and delete nodes, and we're good to go. We can start working with network data. So one thing I noted before is that we're using a few functions on Python lists that are going to slow us down. So in remove node, we called remove on a list. We were also using membership checking in a list directly, and this isn't ideal for Python. So it has to check every element. This is where a different data structure could actually help us out if we have a big network. Of course, again, this is pretty easy to fix. We just want to use something other than lists to store the neighbors. So we could use addictive sets. So here, here's a network where we're using sets instead of lists. So the values are sets, and these are faster to look up, right? A limitation, we also create some limitations, and that we can't have multi-edges here. But you can see to add nodes, right? We just create new sets. So pretty simple, not a lot different. And here to insert the undirected edge, right? We just add them to the set, and we still have to add them both ways. So here we go. We can add an edge between Dan and Carol in our set, and using the sets is actually pretty easy. Again, we don't have multi edges, making a lot of side choices here, and it makes computing something like the clustering coefficient easy. So if we want the clustering coefficient, right, we can just check. We want a function to check if there is an edge, right? And then the clustering coefficient formula, right, is 2 times the number of triangles times the degrees, right? So we compute the degree of the particular node, right? And we compute the degree of the other node and the number of triangles that connect them. So here, this is actually pretty easy. We just have to go over all the combinations. This is where itertools can help us to go over all the different combinations in G of I. Actually makes the code a lot simpler. So this is some nice Python usage here. And if we check the edge, we can go ahead and add to the clustering coefficient. So this is if there is a triadic closure, we're going to add to TI, right? And then we'll divide individually by the KI and the KI minus 1. So divide by the degree. Right, so we can go ahead and look at the clustering coefficient for each node in our network. Here, Alice is 1, Dan is 0, and Carol is 3, or 0.3, sorry. So now with just our single data structure, which was a dictionary or of lists or dictionary sets, and our functions, we really have our own graph library. There's a lot more we need to do though. So computing degree distributions, components, shorted paths, and we need to write a lot more functions. Generally, when we're programming, right, I try to avoid reinventing the wheel and building things that have already been done. So we saw what goes into programming a network, but if we want to do some special calculations, it's going to get more and more complicated, and we might have made a few design choices that weren't ideal. So let's look at an alternative. Networkx is a Python library for working with networks, and it's been around for a little while. It's a pretty mature network package. You can do a lot with it. It's not particularly speedy, but it's well documented, which is important to be useful, and it is in general pretty easy to use. So let's see how we can do some of the things that we coded up ourselves before using Networkx. So first thing to do is import it, right? And we can look at one of the functions in it. So here, read in an edge list. We can just print the docstring directly to see what's available here. So it defines a graph object that we work with. So it'll store a graph internally, and this is really what we did before. So we have, similarly has some methods to make changes to the graph, and let's go ahead and build up the network that we had before. So here we'll define the graph object, add all the edges that we want, and it will create the nodes automatically. So we can see the degrees are the same as what we had created before. So now we can, we actually, rather than having functions which operated on our data structure, here it's an object, so we call them as methods. And Networkx has a lot of different methods. So if we look at all the methods that are available, we can look at the public methods. There's a lot of things that we can do with a network, and clearly we didn't want to write all these ourselves. So you can use Python to explore. This is just a nice way to use IPython to look at what functions are available. So g.order will pull up the docstring for that function with the question mark. Okay, so Networkx provides some utilities for us to read and write networks. We wanted to be able to record files and pass those between programs. So one way to do this is using an edge list. So if you look at the top of this small graph.edgelist.txt, just a simple text file, we have a network defined by its edges. So here, the information is a node, and so node 0 connects to node 2, and this fully specifies a network for us. And here we can specify a directed network. So that was an edge list, right? And another way to look is an adjacency list. So here, small graph adjacency list is just a text file as well, and this is a little more compact. This is actually, it looks a lot similar to the way we defined our network before. So here, node 0 connects to nodes 2 and 3, and also defines a directed network. So you can see that node 2 actually doesn't connect back to node 0, and neither does node 3. So this is just a different way to store it. It's slightly more compact. We saved some new lines in our file here. Another way to store them, and probably one of the more common ways, is an adjacency matrix. So it looks something like this. Here, we're just storing a 1 where there is a connection between nodes I and nodes J. So here, similarly, if you go across, if you go down 3 and across 0, that means that node 3 is connected to node 0. And here it looks like this one is not symmetric, right? So that would define a directed network for us. So yeah, it stores zeros and ones, and again, the position in ij is 1 if the nodes connect. Here, this also gives us a little more power to define edges that have different coefficients than 1. Before, we didn't really have that option, so there's another option with these. Of course, this isn't very efficient because we stored a lot of zeros. So we could also record only the non-zero pairs, and we're back to an edge list, which is an edge list is, thinking about our matrix is really a sparse matrix representation. One of the ways that you would store sparse matrices is our adjacency list. So like a compressed sparse row format is actually very similar. So it gets us back to that. A fancier format, which is defined as an XML-based format, is this GraphML. So it doesn't look like something we're going to want to write ourselves, but it is readable. So this is a common network, the Karate Club, quintessential network science network, one of the first ones people looked at. And here it defines all of the different nodes, and you can define different attributes about them. Here, the name, and also it defines all the edges. So you could define a directed or an undirected network here. This is a pretty flexible format for storing networks. It's XML syntax, as you can see, and we don't have to really deal with reading or writing it. You don't want to deal with reading with writing it, and that's good because Networkx will allow us to do it. So here we can read the Karate Club from GraphML format and print the info about it. So we can store the name, type, and it'll actually give us some basic stats too. Okay, so if we want to use some of the functions that are available in Networkx, the degree, right? You just call that directly on a graph, and it'll show you the degree for each node. This is a list of tuples where the node name is on the left and the degree is on the right. So this means node name 5. 5 is a string, has a degree of 4. Right, the clustering coefficient we can compute using the nx.clustering function. Yeah, it's actually not a method. I'm not really sure why, but it'll give us the clustering on each of these individual nodes. So here it returns a dictionary. And we can also look at some other functions, is connected, diameter, and those are things that we didn't even implement. And of course, we get paths and distances. You can think that this would have been a little bit more work to implement on our own too. So here we can see the shortest path between any two nodes, right? So here, if we wanted to start at 5, right, we can look at the shortest path between 5 and 5. Well, that's just 5. 5 and 16, well, 16 was connected to 5, right? But if you wanted to get between 29 and 5, you had to go 5 to 0 to 8 to 32 to 29. So this actually printed out the shortest path between every node and node 5. And here we can look at the shortest path between 3. It actually gives us the dictionary output. This just gives us the shortest path length, kind of a summary of what we were looking at before. You do have to get the node names exactly right. So here it's actually a string 3. Okay, so we can actually look a little deeper into our network now with Networkx. So one of the things we look at to start is the degree distribution. So if we want to do that in Networkx, we go ahead and compute the degrees of each node, and then we can go ahead and convert that to a list that we can work with. And we want to use a histogram. So we don't actually need to use to bin this. We can actually use counters because we have ordinal values here. So we're going to count this up of the data using some of the handy Python functions and go ahead and make a plot. So this will generate our histogram of our integer data. Right, we use plot.bar. We don't need plot.hist because we don't actually need to bin this. We just want to use integer bins. So here we're just counting the unique degrees. All right, this is what it looks like for our network. The network is pretty small, so our degree distribution actually look kind of spiky. We can go ahead and generate a large network in Networkx and look at its degree distribution. So here, Networkx defines a function to generate a random graph. Random graphs are known as Erdős-Rényi graphs, and after Paul Erdős. And here we generate with 5,000 nodes, right? We can see that the degree distribution here is pretty smooth, right? And looks Poisson, right? So we can look at the average degrees around 5, max is 15, right? And so it actually doesn't have any hubs. We can make another network of the same size to see some of the differences. This is a Barabasi-Albert graph, more commonly known as a scale-free network. And here you can see that actually it's kind of hard to see on this plot. We have some nodes which have no degree. Looks like most of the nodes actually have no degree. Here again we have 5,000 nodes and a similar average degree, but a very different distribution. It's kind of hard to see because some nodes have a huge degree, but some have very few. So we can actually look at this again on a log-log plot. And we can see that this neatly follows a straight line on a log-log plot. And of course, this is a power law distributed network. So moral of the story, we can use our data visualization techniques to really explore networks, look at degree distributions, and we were able to learn some major differences looking at those well-known networks. So there's a lot more we can do with Networkx. We can look at the networks themselves. This is Networkx's default draw function. Just kind of puts them on the graph. And there's a few other functions that it has: draw circular, draw spring. So this uses a spring layout. And We can start to play around with that. There are ways to build nicer visualizations in Networkx, and we'll take a look at that next. In summary, they're very general. Networks are very general. We can represent a lot of different stuff, and there's lots of jargons and vocab, but it should all kind of make sense. You can think about how you would build this up yourself, and it's probably similar to the way it's defined. Some simple ways to represent networks, and these are, again, kind of the mental models that I use, are edge lists and adjacency lists and adjacency matrix. I think working with adjacency matrix is often helpful. And we can also store them in fancier formats, GraphML. So the big network toolboxes, like we mentioned, Gephi, will be able to read and write GraphML as well. And we can use statistics and degrees of nodes to really understand networks. Networkx does a lot of goodies, so I definitely recommend using Networkx to work with networks, at least to get started in Python.